It gives me a great pleasure to invite Dr. Michael Kashmore, uh, who is a Chancellor's Fellow in the Department of Computer Science and Informatics, University of Strathclyde, Glasgow. He received his doctorate from Strathclyde before working multiple years at King's College, London, in the Human AI Teaming Group. His research focus is on domain-independent task planning for autonomous systems with focus on integrated planning and execution, particularly for autonomous robotics. He is currently the lead of Strathclyde Center for Doctoral Training in Explainable AI for Industrial Decision Support, which explores the application of AI alongside humans across a variety of domains, such as telecommunications, satellite mission planning, nuclear engineering, and health. And Dr. Kashmore will be giving a talk on some advanced topics in explainable AI planning, specifically exploring the space of solutions in XAI, as we call it. Um, just a kind of a introduction for AI planning for most of the people who are more familiar with machine learning and the machine learning models and their applications because of their because they are in the news recently, and there are a lot of applications, and you can a lot of hype also around that. But AI is not all about machine learning. When it started in the 1960s, AI planning has been one of the early topics on which humongous amount of work has been done. So there is a lot of literature, it's quite mature, and still there are a lot of open questions in this field. And some of these, so every time, every year, there are no new and new results are being produced, and some Michael is actually at the forefront of this AI planning research, and he will be giving some insights into the research that he is doing now. So after you, Michael, the floor is yours.
Thank you so much for the kind words. I'll share my screen and start the presentation. There we go. I have the chat window open as well. In case anybody has any questions, please do put them in the chat and I'll answer them where it's the most appropriate. I hope there'll be some time at the end for discussion. So as Stuart mentioned, I work in domain independent automated planning. And in particular, I was a member of the Human AI Teaming Group, and now I lead the doctoral training school for Explainable AI for decision support. And one of the things I'm very interested in is how domain independent planning tools can be used to help humans in solving difficult problems. And I'm going to, in this talk, go over a couple of recent pieces of research from my group in Strathclyde and in King's College London to give you an overview of what these kind of tools can do. As so I mentioned, when people think AI, they usually think machine learning these days because of the hype in the news. So I wanted to start with a very fast primer on what is domain independent automated planning. I'll make this talk something between a presentation of my research and a tutorial to introduce you to these concepts in case they're new to you. After this primer on automated planning, we'll look at the first topic in iterative explainable planning. So this is how to explain solutions produced by these automated planners. And then in the second part of the talk, we're going to look at temporal networks and explainable temporal networks in the same structure. First, I'll introduce what is the temporal network, and then I'll present the research we're using to try to interface the temporal networks with human users. So let's start with the first part, which is this really fast primer on automated planning. So short definitions, a quote on automated planning is that it's the art and the practice of thinking before acting. Unlike many machine learning applications, which are are one-shot solvers, which presented with a question will give you an answer. Planning problems are really defined by the fact that they are taking place over time. There's going to be something that we need to do in the future, and we're trying to think about what that should be now. So a longer definition would be that a planning problem means choosing and organizing actions into some sort of structure that we can execute in order to bring about a desired situation. Planning is something that humans do very naturally. Automated planning is just taking that process onto the computer to solve much larger, much more difficult problems in a much shorter time frame. An important note here is that planning is based upon a high-level description of the world that's typically engineered by humans. I'll be calling this a domain model, or a model throughout this talk. And it's this domain model that makes automated planning such an attractive field for explainable AI, because this model serves as a shared vocabulary between the human and the machine, through which explanations can be passed. Unlike machine learning, which is kind of like a black box, in planning we have this model which we can use to help produce explanations. I also mentioned the words domain independent planning as opposed to domain specific. So even within AI, planning is quite a broad field. There are many different kinds of planning. So for example, path and motion planning is very popular, planning how to find your way to a destination, or motion planning, where perhaps you're planning the path that a manipulator is to take on the end of a robotic arm, and you're also considering all of the collisions that robotic arm might be making on the way. Communication planning, grasp planning. There are many different kinds of domain-specific planning. And domain-specific means that the models are well understood, specific to a particular problem, and we're going to use a solver that's specific to that kind of problem. We're going to use a path planning algorithm to solve this problem. Domain-independent planning, on the other hand, instead uses a solver that works with a kind of general formalism. We have a formalism that we use to describe our model of the world, our planning problem, and we can use any off-the-shelf solver to then solve that problem. The advantage of this is that we don't have to prescribe anything about the domain. Instead, we just need an engineer to write the model that any solver can then be used upon, which is obviously going to be much more reusable, and you'll get the benefit of improved solvers year after year. Within domain-independent planning, of course, there's multiple kinds of features your problem might have, and I've bolded two down below, because these are the features that I'm most interested in, and that will be part of the problems I'm showing you today. So the first is your problem discrete or continuous? This means, is the description of the world in which you're making these actions and searching for a plan a set of discrete variables, perhaps Boolean propositional logic, or do you also have real valued variables such as resource, like real valued resource or time? This makes a big difference to the kinds of solvers you can use, because as soon as you have a continuous space to search within, you have an infinite number of states to search through. And secondly, sequential or temporal, and I'm interested in temporal problems. In a sequential problem, your solution, your plan, is going to be a structure of actions that looks like a sequence. These are the two things you must execute, and you must execute them in this order. That's very simple. A temporal plan is more complex. Instead, actions have some duration, and they can act concurrently. And many domains, especially the ones I'm interested in, are really concurrent temporal domains in which there are processes that are going on all the time. In that case, the structure of actions, the plan that you've produced, is going to be a more complex structure than a simple sequence of actions. And the second part of this talk, temporal networks, is one such structure. So we'll look at that later on. This is just to give you an idea of the breadth of what planning is about. And I have an example problem, which we can look at quickly. You should be able to see a SSH client popped up here. Inside this SSH client, I have an example planning problem and an example solver here in green. please let me know if you can't see it. And I'll show you just briefly what the syntax looks like. Thank you, sir. So this is a problem called simple satellite, which is a simplified version of a real domain that's used, benchmark domain, to schedule satellite operations. In this simplified version, you have images that need to be taken by the satellite and stored in a memory bank. Inside the memory bank, they need to be analyzed before they can be dumped to a ground station, and all the while the satellite is moving. So images can only be taken within certain time windows when the satellite is above the target, and they can only be dumped when the satellite's above the ground station. And the goal is to sort of maximize your reward by taking as many pictures as possible. And you have these actions: take image, analyze image, and dump image. And ignore the rest of the syntax for now. So then I might try to run a solver, and very quickly it will produce me this solution. This is the solution produced by the solver. In this case, the first number here is the time at which the action should begin, and the second number is the duration that process will take. So taking the image will take this amount of time, and it should begin at this time. And then in the middle, of course, is the actual action that's taking place. And this is one possible solution for this problem. The planner was able to generate it relatively quickly, 3/4 of a second. But there may be better solutions, maybe other solutions. But the 2 points here. First is that the planner generates this much faster than I could by hand. And the second is that this is perhaps not exactly the solution that I want. And what to do in that case is really what I'm going to talk about in the next part of this talk. Okay. So the formalism I just showed you is the planning domain definition language. It's one formalism for describing planning problems. The planning domain definition language contains a description of how the world behaves and what are the capabilities of the agent, whether that agent's an autonomous agent that's going to execute the plan, or whether it's a human that's meant to carry out the actions. You might be producing plans for logistics scenarios where deliverers are actually humans delivering packages, for example. A description of the initial situation, what is the state you begin in, and a description of the desired situation. And your problem is then a search problem to find a path of actions from one to the other, or some structure of actions. And just to simplify things a lot, I really won't go into more technical detail than what's on this slide. I think this is sufficient. You could describe a planning problem with these set of variables, a set of Boolean propositions. So here we have a discrete state, a set of deterministic actions with no uncertainty. Your state set, your search space is then the power set of your propositions. Right? Every possible assignment of those propositions is a unique state through which you need to search. So you can see the problem size is exponential in the size of its description. Your initial state is a singular state, in this case, and your goal function is a function that maps states to whether or not they hold the desired property. And each action is simply a condition that must apply for the action to be applied, and the effects of that action, which propositions are deleted and which are added. So that will take you from one state to another. Okay. And given this relatively simple formalism, plus the extensions for times and numbers, which I don't want to go into, we've managed to apply automated planning successfully to a wide variety of different domains. It's quite a cross-cutting tool. So, for example, here is a sort of snapshot of the different projects I worked on during my time at King's College London and now Strathclyde. So, for example, we've used planning in the top left there for situational awareness on shipping inside the English Channel. Down on the right-hand side, we have indoor robotics, so a mobile robot meant to tidy a child's room and interact with human children. Used AI planning as the core to decide what this robot should do. Whereas below that, we have autonomous underwater vehicles, entirely different kind of domain, where there's no human interaction at all. And in fact, the agent has to be robust and resilient in order to make sure it's not lost. On the bottom left, yet another kind of domain, We used AI planning for urban traffic control in London, working with Transport for London, where we used planning to understand what should the timing be on the traffic lights in order to reduce congestion in the face of unexpected events, for example, a bridge closure. And these plans weren't then applied automatically to the traffic lights, but instead given to the human operators who work for Transport for London. They used the planner to give them ideas on what solution they wanted to enact by hand. So you can see there's sort of a wide variety of the domains in which planning is used and also the way in which it's used. And I'm more interested now in this talk about the latter kind, the Transport for London example, where humans are an integral part of the planning process and also enacting that plan. And I'm less interested in the underwater submarines where everything is really out of the hands of the humans. Okay, so let's go back to that plan just for a moment. So just now that I've given you a very quick view on what PDL looks like, you can have a look at this domain again. You can see here we have our set of predicates. This is a first order definition of the propositions of our domain. These are the things which can be true and false. And here are the actions which will make, this is the condition that must hold in a state for the action to be applied, and then these are the effects. So it makes this fact false, makes this fact true, and so on. I don't want you to worry too much about understanding this domain yet. This domain, you'll notice, specifies the actions and the propositions and the types, but not what is the initial situation and not what is the goal. It's just these things: types, the facts, functions are the real numbered variables, and then the actions. And these domains are typically written by a human engineer who understands the domain very well. This is the part of the puzzle that needs to be validated and verified and will be constantly updated when flaws are found. The other part is the problem file. And this is just describing the initial situation. And typically these are automatically generated if you have the data. And I'll probably refer to this as a problem file or a problem instance. This is one instance of the problem within this domain. In this case, we have these memory slots. We have these images or target images to take. And here are the time windows describing when these images can be taken and not, and when this data can be dumped and not. So given this domain file, which the engineers trust, and this problem instance, which is more or less a trivial list of the current data, the planner generates this plan. And if I were to study this, I would start to ask some questions, right? My first question when I looked at this plan, I've seen it before, is why is there such a large time gap between this action and this one? After the last image has been analyzed, almost double the time, almost the half of the whole plan is simply waiting to dump the final image. That seems very strange to me. Also, I noticed that 0, memory slot 1 because 0 is filled, memory slot 2 because memory 1 slot is filled. Then everything is dumped and it takes the next image into memory slot 1 and not memory slot 0. I'm not sure why that is. When you're confronted with a plan, what a plan is a communication of intention. This is a description of what the planner says we should do to bring about the desired goals. But it's not a description of why we need to do these things. There's no reasoning behind these actions. It's not providing any justification. When given something like this, it is very natural to want to ask questions and queries. Even if we trust the domain, we still might want to understand why this is the plan that was selected. And this is why explainable planning is an important topic. So I'll move into the second part of the talk now and look at explainable planning. So explainable planning has really exploded the last 3 or 4 years. And on the left-hand side here, I'm showing a link to the website for the Explainable Planning workshop for the last couple of years. which is where a lot of the, for me, the most exciting developments have been taking place. And that website has a section called the Landscape of Explainable Planning, which I didn't write, but I want to present to you in a simplified form in these slides just now to give you an idea of the kinds of explanations and approaches to explanation that can take place. So on this website, they break explainable planning down into sort of two categories: explanations for plans and interpretability. Interpretability means the way in which we generate the plan will somehow embed explanation within it. When you look at the plan, the actions that will be taken will be legible, meaning you kind of understand the reasoning behind the actions as well as the actions themselves. That means that the way in which we're going to write our domain model will sort of be written with explanation in mind. On the other side, explanations, we're going to take solutions that were generated from any domain model and attempt to provide explanations for those to humans. And that's what I want to talk about here. So underneath explanations, there are many approaches to explanation and things that might need to be explained. So for example, are we trying to understand how the planner is working and explain the algorithm that's being used? Or perhaps we have an unsolvability, that we ran the domain and the problem through the planner and it reported that there was no plan that achieved these goals. Well, that's no good. Probably these goals are to achieve something important for our business. For example, we need to know what to change in order to make those goals achievable. Did we need more money? Did we need more time? Did we need more bandwidth, perhaps? If we can ask that kind of question, then we know what we can do outside of the planning world and in the real world in order to make a solution. The kind of explanations I'm looking at are explanations that use that domain model as the medium for communication. We know how cause and effect works because it's written explicitly in the domain model, so we can use that to extract justifications for actions. Within that, this website then lists inference-based and reconciliation-based types of explanation. I'll be looking at inference-based, but I want to mention reconciliation-based explanations, which I think is a very interesting idea first, and also a very good concept to understand why having a model is so good for explanation. So reconciliation-based explanations. The assumption is that the system has one domain model, but the human user has a mental model of the way the problem works. I think that's reasonable. Even if we're not a complete expert, we probably have an idea or an intuition as to what are the effects of actions and how we might accomplish some task. Now, when the user thinks that there's something strange in the solution produced by the system, the assumption is that this is because the mental model of the user is different from the one used by the system. And an explanation is an update to one of these models that brings them closer together. If they're exactly the same, there's no longer any need for explanation because you have understanding. I noticed that I said an update to one of the models. Explanations don't just mean that the human's mental model gets updated and they understand the problem better. An explanation can also reveal that there's a flaw in the model, or an explanation can reveal that the model is acting outside of its area of competence and might need to be expanded to handle some new situation. Okay. On inference-based explanations, what we're going to use is the model as a tool to understand the cause and effect, as I mentioned. And the work that I'm going to talk about in this section is presented in this journal paper, Contrastive Explanations of Plans Through Model Restrictions. The first author, Ben Crarup, may be in chat to answer questions as we go along. And this is work that he's carried out as part of his PhD thesis in King's College. Okay. So as I mentioned before, the need for explanations really arises when there's a mismatch between the plan and the expectation of the user, perhaps because the user's mental model is different. It could also be because the user doesn't have the computational capacity inside their brain to produce a solution or to produce the same solution that was produced by the system. It could also be that the user has preferences which aren't accurately modeled by the domain model, or aren't modeled at all. And this is very common. It's very difficult to model a goal correctly. And an explanation is an attempt to bridge the gap between these mismatched positions. Where our approach differs from the model reconciliation is that we don't treat the explanation as a token that's passed from the system to the user to bring the models closer together, but instead we think of explanation as a process, an iterative process that actually takes multiple steps in order to bring understanding. It's fairly hard to see, but this is a loop on the right-hand side. And this is our explanation process as an iterative process. The user will ask a question and receive an explanation from the system, and this will repeat over multiple time steps. On the left-hand side is a diagram of what's actually been implemented. Basically, we have using the planner as a tool within this larger architecture to produce explanations. Okay. For now, I want to just talk about how one step in the system process is done. How does the user ask a question, and what kind of response do they get? And then I'll explain how the iterative process brings this together. So what is a user question, and what is a contrastive explanation in this case? So in the journal paper that was referenced previously, we ran a user study to understand the kinds of questions that users will ask when presented with plans. And we gave them 3 very different domains, and we just wanted to try and understand, when presented with a communication of intention, what are the natural queries that a human might have. And we find overwhelmingly that users weren't interested in understanding how these actions were to be carried out, but rather why these particular actions. And this was broken down further into this set of questions made by Ben, a taxonomy of contrastive questions for automated planning. By far the most common is asking, why is this particular action in the plan? I asked that already. I said, why is this image loaded into memory slot 2? You also have questions, why is action A rather than action B? And also temporal action. So why is action A outside of time window W? I asked that, in fact. I said, why is there this huge amount of time between taking the image and dumping it to a ground station? Why not do it earlier? Ordering questions between actions, and somewhat less common things. Why is an action within a time window? Or why did you do this action now rather than later? All of these questions I call them contrastive, because what the human is doing is saying, this is what you did, this is what I would have done. They have a contrastive case, sometimes an explicit one. Why did you do A rather than B? And sometimes it's implicit. Why did you do A rather than not doing A? And the second part is unspoken. But in each of these cases, the user is not just asking a question, but providing a suggestion. This is what I would have done, or what I would have expected. So the way in which we can present an explanation is to generate the plan, or attempt to generate the plan that the user would have expected. And this is what I mean by a contrastive explanation. Okay. So the way in which that is done, I don't want to go into details, but new constraints are added to the problem in order to force the user's suggestion to be a part of the plan. So fulfilling that user's suggestion becomes a part of the goal that the solver must complete. And the plan that's produced, we call the hypothetical plan, now is closer to the one that the user expected. And now we can compare these artifacts directly. Here is the original solution, here's your solution. And a very simple way, explanation would be, well, if we did it your way, it would cost more. Swarov asks in the chat, what about unsolvability and actionability questions? That's a very good question, because one of the reasons the user's suggestion is rejected could be, if we did it your way, there is no solution. The problem becomes unsolvable. And that moves you in that landscape of explainability to that unsolvability section. How do you explain unsolvability? It's very unsatisfying for me to tell Swaroop, I didn't do it your way because that's impossible. Because obviously Swaroop doesn't think it's impossible or wants to know why it's impossible. That's why he's asking the question. I don't want to go into how to explain unsolvability right now. Perhaps just to give you some intuition of one way it could be done. This is from the same group as who made the landscape of explainable planning. That's ASU. They create an abstracted, simplified version of the problem and attempt to solve that. If it's unsolvable, they repeat the step until it's so abstract and so simplified, they can produce a solution. And then what they show to the user is the thing that they abstracted away. They said, okay, we abstracted away this detail and now we were able to solve it. So it's these details that are making the problem unsolvable. And of course, it's a bit more nuanced than that, but it gives you an idea of a way you might explain unsolvability. Okay. Now, I mentioned that by adding these new constraints to the problem, according to the user's suggestion, we bring the solution closer to what they expected, but it might not necessarily be exactly what they expected straight away. As I mentioned, it's very hard for a user to specify exactly what is their goal and what is their preference, even if they're given this modeling language to be able to do so. So we're going to put this contrasted question and answer process within an iterative process where the user can continuously ask questions and refine the plan. So for example, given a plan, a problem pi, this CP, that refers to the computational capacity of the system, and it's a function on this problem that produces the solution that the planner generates. So given the solution, the user comes up with this question phi1 or constraint phi1 that's applied to the problem. Okay. And that's the first interaction with the system. And from this is generated a new problem, which is the original problem plus the new constraint. A new plan is generated, and this leads the user to a new question, either a different topic, or they might say, well, that's closer to what I expected, but although you applied the action that I asked for, you didn't use its effects. You kind of applied it in a redundant way and then did the thing that you did originally. I want you to not do that and use the action that I asked for. So they have another suggestion, and it builds on top of the original one. So it's applied in addition to the previous constraint and leads to a new plan. And at this point, the user says, oh, I see now, I understand why you went the other route instead of this route. But I have another question, and this question occurs to me because I've seen this new plan, but it's built upon the original one. So you select, again, the root node in the tree or any other node in the tree and apply the constraint. And gradually you build a sort of a large tree of different solutions as the user asks more questions and applies new constraints. And this will eventually converge to one of several outcomes. Either the user becomes satisfied that now they understand the original solution, they trust the original solution, or perhaps the user has now identified what it is about the model that's incorrect that they can now fix, or the user has recognized, has managed to force the planner to generate a plan that conforms to their preferences better than the model does. So the final plan that the user is satisfied with could be the original one that now they understand better, or it could be any of the other nodes in the tree. The user has used this tool in order to iteratively generate better and better solutions for them. On the left here, I say that this iterative exploration can converge upon any plan, and this is technically correct, but practically it's not. Especially when you have discrete and continuous space. If you have an infinite search space, it could take you infinitely long to converge upon exactly the plan that the user wants. And if you have a temporal domain in which actions can be scheduled at any time point and have different durations, you again have an infinite number of solutions even inside that infinite search space. So I would say that it will converge eventually for the user, and it will only converge if the solver is able of actually solving the problems with all of the additional constraints that the user has added. Sometimes these constraints can make the problem easier by the problem harder, especially when the heuristic guidance from the search algorithm doesn't really conform to what the user wants. Their preferences are so different from what's modeled. So this iterative search is a very clumsy way to explore the space of solutions when you have real valued commodities such as temporal actions, risk, if you have any uncertainty in your domain, and I'll talk about that soon, and time-dependent costs, or any kind of real valued costs. Okay. So what we did, what Ben and the rest did in King's College London for this iterative contrasted questions is a very good way, and the key phrase here is to explore the space of solutions for a propositional planning problem. And that's the way we see explanation. It's not, as I said, not a single token with a piece of information, but it's a way for the human to explore the space of solutions, to better understand the problem, and to find a solution that suits them the best, whether that is understanding the original solution or creating a new one. Okay. Now, moving into continuous state and temporal actions, we're going to look at the different formalism and how we might explain that. So I'll just remind you, I'll give you a very fast primer on temporal networks, and then, since I've used a lot of time, a very fast explanation of how we allow the user to explore the space of solutions for these kind of problems. Excuse me. Okay, so if you're not familiar, a simple temporal network is a fairly trivial formalism. It's a set of time points which are real valued and a set of constraints of this form. And a solution is a schedule that is an assignment of time to each of the time points that satisfies all of your constraints. Any of you who do linear programming, I imagine most of you are familiar with linear programming. This is a very easy linear program set up here. You have a set of variables which are your time points, and all of your constraints are of this form. T minus t is less than or equal to y, tj minus ti is less than or equal to x. Typically, we'll represent our temporal network as a graph when we're presenting it to a user. This just means that each of these nodes is an action or an event that's taking place in the plan. For example, the start or end of a durative action. And the arrows represent temporal constraints between these actions. And this is, on the right, is an example plan that was produced for one of the mobile robots, the one that was meant to tidy a child's room that I showed you previously. And I sort of zoomed in on a part of it here. And in this case, you can actually see there's actions that's intended for a human to be performed, like human go to waypoint, human go to waypoint end. This is really just to illustrate that even though we can represent our temporal networks as graphs, that doesn't mean that they don't need explanation. You couldn't put this in front of a human user and say, here's the plan. I assume there's no questions. There will obviously be some questions about, well, first of all, what's the plan? But this is just the graphical representation that I'll be using in the following slides. Now, simple temporal networks are a great way of moving away from that sequential, single deterministic action-based plans into a more complex structure that allows you to represent durations of actions and allowing you to do things concurrently. Okay. But the main limitation for us is control. It assumes that every single time point can be assigned some time in order to generate a valid schedule. And in fact, that's not the way the world works. I can choose when to start, let's say, sending the data or dumping the data from the satellite. I can't choose when that ends. It will depend upon the speed of the network, for example. I can choose when to start moving towards the waypoint. I can't choose when I will arrive at the waypoint. It depends how busy is the corridor. So there are time points which I don't have control over, and my schedule is not going to be robust to this kind of uncertainty. So in that case, we'll upgrade this formalism to include uncertainty. We'll have simple temporal networks with uncertainty. These will split our time points into those which are controllable and those which are uncontrollable, whose values will not be decided by me, but by nature. It will split our constraints into a set C, which is the original constraints, and a set G, which is our contingent links. These contingent links are of a very similar form. We're saying that there is a controllable time point and an uncontrollable time point, and they're linked by some lower and upper bound. The only difference is semantically. This is not a lower and upper bound I can choose between, but this is what I expect nature to choose. Right? This is the random interval from which a duration will be sampled. Okay. And my solution is no longer an assignment to all of the time points. It's an assignment only to the controllable time points, and it can be as a function. It can be as a control sequence. So I no longer need to upfront decide all of my time points, but I can instead specify an algorithm that will execute this network and react to the uncertain outcomes of these contingent links. Okay. Now I'm going to be most interested, though, in the simplest such algorithm, which really is a schedule to the controllable time points that is nevertheless robust to the outcomes of the contingent links. So I'll quickly describe what that means. So first of all, you can think of an STNU, the simple temporal network of uncertainty, as being a collection of simple temporal networks. Each contingent link has can be projected into one of its realizations. So here, for example, this contingent link between T0 and T1 is projected. We observe that this duration was exactly 6.456. But for every possible projection, that's a different STN. Okay. If we project all of the links, contingent links in our STNU, we'll end up with an STN, which will have some solution, we hope. Okay. What we're looking at is an assignment, a complete control sequence, that is an assignment of times to all of our controllable time points that is valid for every possible projection of the contingent links. So before we've observed anything, we're going to assign a schedule to all of our actions and say, this schedule will be robust to uncertainty in the future. That sounds like quite a demanding property, and it is, but actually it occurs more often in real life than you might expect. It's only when deadlines become very tight that you might have to start reacting on the fly and performing contingencies. Typically, you can generate a plan in the first place that you know is going to have a strongly controllable schedule afterwards. Okay. Right, so now we have a simple temporal network of uncertainty, and I'm afraid they also have some limitations. And the main limitation here is, how do we model those contingent links? Who decides what is the lower and upper bound on how long this uncertain event is going to take? Our domain expert can give it a good guess, but if in reality it's going to take earlier or later, we're no longer guaranteed to be robust against this uncertainty. So really, what we want to do is to collect data to make a more accurate representation of the uncertainty of these uncertain durations. And in particular, we're going to model it as a probabilistic simple temporal network, which looks very much like a simple temporal network with uncertainty, but we replace those contingent links. It should be a D here. We replace this set of contingent links with a set of contingent links represented by probabilistic distributions. Okay, so for example, a normal distribution or something drawn from data. And the solution is exactly the same. Okay. Now, the main difference between solving a probabilistic temporal network and an STNU, where we have the uniform bounded uncertain links, is that the probabilistic distributions can be unbounded. And so it might be completely impossible to create a strong solution that is always going to be successful. But that's only because we're thinking about these extremely unlikely tails of the distribution. And in practice, it makes a lot more sense to say, well, we can create a strong solution if we ignore these tails. If we only take a look at 99.9% of this probability mass, we can create a strong schedule that will be robust against it. So why not? So we can trim the tails of this probability distribution and only deal with what remains within this lower and upper bound. And in essence, what we're doing is we're transforming our probabilistic simple temporal network and turning it into an STNU. If we do this for all of the probability distributions in our network, then we transform the whole PSTN into an STNU, and we can solve it in the normal way to create a strong control schedule for that STNU with an associated risk. And that risk is how much of the probability distributions we're now ignoring. Now, there's multiple ways of calculating what that risk would be. Typically, inside a solver, most solvers that I've seen so far have been using Boole's inequality. You simply upper bound the risk by summing together all of the trimmed parts for the probability distributions and then try to minimize that. And this gets you what we call a chance-constrained probabilistic simple temporal network, which is in essence an STNU. Okay. Now that's the formalism we're going to be using to explain, to describe our plans. The output from our automated planners are going to be of the form of a PSTN. And then we are going to chance constrain it by trimming away the ends of that to create a strong schedule. So here's an example output from a planner. This is the plan that was produced for rerouting network traffic within a data center. This is some work being carried out at Strathclyde by one of my PhD students. So very simply, we start here at B0, that's the start of the plan, and we need to reroute network traffic from pod 2 to pod 3. And that's going to start happening at B1 and it finishes happening at B2 and takes exactly 5 time units. At E1, violation of a service level agreement, and we need to have finished rerouting before that happens. At E2, this violation ends, and after it ends, we need to reroute back to pod 2. Okay. So you can see that's sort of the ordering of things here. Okay. The 2 red arrows here, the beginning and end of this SLA violation, those are predicted, but we don't know exactly when they're going to be. Instead, we have some probability distribution here. And importantly, also on this this node here, we have a strange blue arrow. This is a relaxable constraint. We can actually start migrating earlier, but at some cost. And this is quite common to find as well. Like a constraint is not a hard constraint, but rather you can start to extend that constraint at some cost. I can delay a deadline, but the longer I delay the deadline, the less return I'm going to get. SWOP asks, are the explanation queries the same or different for plans or STNUs, or different from classical plans? I'll actually answer that in a couple of slides, so I'll come back to it. Okay, we want the strongly controllable solution, and we can do this in 2 ways. We can squeeze the probability distributions, these 2, until the solution becomes strongly controllable. But of course, the more we squeeze those distributions, the higher the risk that, well, actually now we're risking that the whole thing will fail. We can also relax the resource constraints to increase the cost. If we relax the resource constraints, we're able to squeeze less and still get a strongly controllable solution. So what we have is a bi-objective problem here. We have risk versus cost, and these things are not directly comparable. And in fact, the real solution, when to schedule these time points, means picking a cost and picking a risk that the human operator, the supervisor, is happy with. Rather than saying, here's one option, what we really want to do is exactly what we did with the explainable planning. We want to show them the space of options. And of course, with bi-objective optimization problems, this is more or less a well understood thing. We use the epsilon constraint method to generate the Pareto front of solutions here. We say, well, here are your options. This is the best we can do on risk versus cost. But conceptually, I want you to understand that this is what we were doing with the tree of solutions in the discrete problem. The tree of problems is allowing the user to step through a set of solutions. This is the same. Okay. Now to tie these two things together, and really to answer Swarop's question, is how do we tie these things, how do these things combine into a single system that makes sense to a user? One possibility would be to generate a solution with an automated planner, allow the human user to start asking queries to expand this tree and explore the different options. And for each of these solutions, generate the Pareto front of how many objectives there are for that solution. And this is the most straightforward thing to do. Okay. Things that we haven't done include these three bullet points, which I think are much more interesting questions for future work. The last one, I believe, is answers your question, Swarop, is are the queries the same or different for STMUs and for plans? I would say that they can be different. That I could ask, if you give me the Pareto front that shows cost versus risk and versus other constraints, I might ask or think of questions whose impact will change the original plan that was generated. Okay. If you give me a front that looks like this, and you say, well, if you want to, no more than 0.5 risk, then the best I can do is 35 cost. I'd say, well, that's for this plan. Actually, could you generate me a different plan which has a different Pareto frontier? I'm willing to accept a little bit more risk here or a little bit more cost here, if you can find me a curve that looks different. So in this point here, plan explanation, continuous spaces, I think what's important is to be able to have questions and constraints that come from the continuous explanation and then apply that back to the original planning problem to generate a new structure of actions that can have a potentially different set of schedules and set of optimization solutions. Okay. And the other point, I can let you read them here. I think I'm running a little bit late, so I have 5 minutes left for questions, if anybody has any questions.
Thanks, Michael. Very excellent presentation and a lot of insights packed into few slides. I think at least the beginning part would have given good introduction to people who would not have background in AI planning, and those who know. I think the next part, the second part of the talk, would have given very new insights. There would be definitely questions about the explainability and planning, because people have been in machine learning. A lot of people here are from machine learning, and then machine learning explainability is kind of that's also a very hot topic. So it would be interesting for these people to know that the same type of questions or the concerns are there for the classical problems with twist, of course, here. like AI planning. Uh, so I could start off with one question, and maybe there will be other questions, and this is directly related to the relation between trust and explainability in the context of planning. So here we are talking of plans and planners. And the thing that you told about the questions queries were about a produced plan. So the question whether you believe that this plan is correct, and why not some other plan? Why is it the most optimal, etc. So this is about the plan itself. Uh, does it give any confidence or explanation and hence trust into the planner, the algorithm itself?
Actually, I can answer this. So my colleagues at King's, those who went on to uh, let me scroll up. But the middle one here are some of my colleagues at King's now working for Schlumberger on the world's first fully automated oil rig. They have some practical answer to that question, which is over time, the user does become confident and start to trust the solutions produced by the planner. So they do trust the system, they trust the domain, they trust the planner. And this is something that's not built over one episode, but trust is built up gradually. And the number of questions that they ask about the plan decreases gradually as they start to pass responsibility to this. Whether that's a good thing or not is a different question.
Mm-hmm. Okay. One quick question, because I'm becoming greedy, but let me ask this question. I hold fort now, so even going through the large plans may be difficult because the way you presented gave the feeling that the plan is output and one can actually go through that and then pose this kind of explanation questions. But if there is a 1,000-line plan, for example, or a big DAG, then even going through that is difficult. So what kind of things can be posed to force or the help the person to focus on certain parts which may be critical?
So there is work on this. None of it is mine, unfortunately. But if you go to the Explainable Planning workshop page, I'm sure you can find some things. In particular, on plan verbalization and summarization. So I mentioned creating abstract problems, abstract solutions in order to show why something was unsolvable. But you can use the same idea to create summarized versions of plans. So instead of giving you all of the details, I'll give you a very high level overview. This is what the plan will be. And then I will allow you to direct the conversation and create more detail. So you can point to a part of the plan and say, okay, give me more information here. So I know you're particularly familiar with strategic tactical planning. It's actually a very similar idea. Plan verbalization is a different idea, which is to pass the plan as input into a new system whose output will be a natural language description of the plan. I'm less familiar with exactly how that works.
Thank you very much. I think I will leave it to the audience to ask more questions to Michael. You can directly ask here, or you can raise your hand and the coordinators will schedule those questions.
Can I ask one, Sarup?
Yes, please go on.
Thank you, Michael, for a brilliant, nice talk. My one query is that can explainability be complete for a propositional planning problem? I think
It's a hard question to understand. What does it mean for an explainability to be complete? Would that mean that it's always possible for the human to fully understand the problem and the plan. In which case, I think the answer would have, to be no.
You had one slide telling what, when, this type of queries somebody can ask. So I was thinking that, a system, planning system, can there be suppose I'm designing another system which to explain a planning problem or a problem synthesis of a problem or a planning. So in that case, can the explanation system be complete?
So we had this conversation in our group. That this table is most common questions. It's not a generator set for all possible constraints. Okay. What would be really nice to have is a set of user questions from which any constraint can be built, and so any plan can be generated. And if I understand your question correct, is it possible to create such a set of atomic questions whose combinations are then able to converge upon any possible plan? My intuition says yes, but I have no proof for that.
Okay. Because even there is the verifiability of suppose like a relational algebra, it says that it is incomplete, to find out all possible relations, from given set of relations.
So our advantage here is that we only need to be complete with respect to what's possible in the planning model. So we only need to be able to describe constraints that are in the syntax or the semantics of PDDL, for example. But that also assumes that any constraint that the user wishes to enforce can be described using PDDL. So
can I?
Yes, but we do talk about optimization also in the planning. So I think that will be combine that with the logical problem, then that might kill the, I think, nice any kind of completeness.
Yeah, if you have this where you can extend restrictions on the planning problem to include new constraints on cost and risk, we're now outside of PDDL.
Yeah.
And my intuition says that it's not possible, but I don't have any proof. That's a good question.
Yeah. So can I have one more query?
Yes, we have time. Please go on.
Dr. Michael, you talk about the domain-specific language, So do you think that for an explanation, we should have a domain-specific ontology for a domain, for explaining a planning problem for a particular domain? And how practical it is to have such system?
I think that it's very useful to have that. If you have any additional data or machinery you can use specific to your problem to explain plans or to interface those plans with humans, that's obviously good. How practical it will be just depends on how much effort it is to produce it.
Yep. Yeah, in some limited domains, we have actually done that. So you have ontologies, and planning is done only a part of the propositions to build the state space, and only those propositions, the values, etc., they are obtained through the ontological inferences, because
Do
And
you have something like, what we have, object constant language, OCL? Do you have something like that for planning also?
Sir Mike.
I'm not familiar with OCL, so I don't know what the answer is. Say object constraint language.
OCL, they call it, so they particularly give a domain specific language and to construct the specifications for objects using OCL. I was just talking about this.
Right. Yeah.
Is it there? Something like that.
Yes. So I mentioned PDDL a lot. Many of the formalisms for planning, most of the formalisms for planning are similarly declarative languages where you're just specifying the constraints. Importantly, you're specifying constraints that happen over time. There is an addition to PDDL which looks very similar to OCL. I'm looking at some examples here where you can specify what we call axioms, which are really entailment and implications within the state space. And these are an add-on to your domain that allow you to quickly make new inferences.
Do you think that such thing will evolve in time to come? Suppose like a planning construct language or something. So where explainability will be built
I think explanation is really driving new work in these kind of entailments. There's a group in Germany who are working on what's called plan property entailment for explanation, where what they're doing is searching for new entailments within the problem and using those as explanations of why certain things was done. So I ask, can you please give me goal A and goal B, please? That problem's unsolvable. And the explanation is, well, A implies not B, B implies not A. These are two entailments that we've discovered. Excuse me. And these can be, broken down and can be used to describe these sort of axioms of the problem.
You have nicely, gone from something like, descriptive to quantitative, in your explaining, I could see the nice transition. You started with domain-specific language and, then it came to the distributions, and nicely the whole story, explaining story is built up. So I like the presentation, Michael. Thank you.
Thank you very much. It's kind. I hope it was interesting and enjoyable.
Yes, I think it must be. I think people will start looking at new fields, not new fields, fields other than machine learning, and definitely there are a rich body of work.
What really needs to be looked at is how these fields can be joined in the most useful ways.
So one little, Dr. Saurabh, before ending, to Dr. Michael, the connectionist model, there I find like neural networks and all. So do you think these systems can be also, the explanation capability can be built into those systems? Because they are looks like, they are totally not deterministic, or you don't know what is black box type, what is happening inside, so
I mentioned the situational awareness domain. That was actually an explanations domain combining machine learning. We were trying to use planning to explain the output of a black box neural network. So we have a very large problem of spotting unusual behavior in ships that's too large to solve without machine learning, let's say. The machine learning would output that this ship is acting suspiciously, and the human user would say, why would you say this? Rather than return to the neural network for an explanation, we now model the very small local problem of understanding the behavior of a single ship as a planning problem, and then use planning explanations to say this action that this ship is doing is suspicious because it looks like it's pursuing this goal, for example.
Okay. Thanks. Thank you. I could.
Interesting.
Maybe, I mean, that situation, once it is a visible situation, I was thinking maybe in the inside, little dip. Before that means that situation states, we know those states, before designing explanation. So, but in between also what inside goes on, many things. I was thinking in that way, can it be dynamic? The something like like you have the alerts, So similarly, or any constraints you put it satisfied, then alarm comes. So like that in a connectionist model, can there be something like that?
I think food for thought probably.
Yeah.
That, yes. I think in the interest of time, we may close it now. We are a little over time. So if there are no other questions, please raise your hand, your last chance. Okay, 1, 2, 3. Okay, yes, no questions. So I think we will give a grand applause to Michael for the great talk, beautiful talk. I think people can contact you definitely, Michael, for any kind of
Yes,
questions
please.
or clarifications later. And then the contacts will be here. So please use him.